So in this video, I'm going to introduce what an exponential and a logarithmic function are, and then we're going to have some applications with interest compounding. Okay, so let's start with exponential functions. So an exponential function is any function of the form f of x equals b to the x, where the variable is in the exponent. The difference between an exponential and a polynomial is that the variable in a polynomial is actually in the base. So here, b is the base and x is the variable. It's the argument of the function. We require that the base be positive, so b is greater than 0. The domain of f, so the set of values that x can take, is the entire real line. X can be negative or positive or 0 or anything as long as the base is positive. The range, so the set of output values for f, is just the set of all the positive real numbers. Note that f of x is never going to be 0 ever, and as long as the base is positive and we have a domain over the whole real line, we will always have a positive output for f. So 0 here is not included in the range, and we note that by having an open parenthetical expression on the left. So for all x, the identity relation 1 to the x equals 1 will hold. And for all b, b to the 0 will also be 1. So there are two identity relations associated with this. There are several rules for exponential functions that are important to remember. Basically, when you have multiplication of the bases, you can just add the exponents as long as the bases are the same. So if you have b to the x times b to the y, you can write this as b to the x plus y, and this is the multiplicative rule for exponentials. The quotient rule for exponentials is very similar. If you have two bases and two base functions that are dividing each other, you can just subtract the denominator exponent from the numerator exponent and write them under one single base. Finally, there are power rules for exponentials, and they essentially tell you how to deal with raising the exponential function inside a parenthetical expression to a higher power y. So here we have b to the x being raised to a higher power y. Well, you just multiply the exponent on the base inside of the parentheses by the higher power to which you're raising it, which is y. So this applies also for distribution when you have two separate bases. So suppose a and b are not the same. If you have an a and b inside of a parenthetical, you're raising both of those to the x. This is equivalent to writing a to the x, b to the x. Logarithmic functions are just the inverse of exponential functions. So if b is greater than 0, the expression y equals log bx is equivalent to x equals b to the y. So in this case, what we would have is we have, say, f of x equals log bx, log base bx, and then f negative 1 of x equals b to the x. So these are inverses of each other. That means if you compose f of negative 1 of x, you're going to get back x, and that's the same if you have the inverse function be the outside function in the composition. So the domain of f, in this case, f is log base b of x. So let's let this be f, is just x between, any x between 0 and off to infinity. That means we cannot define log base b of 0. So logarithms cannot take non-positive numbers as inputs. That means the domain is 0 to infinity. And that means the range is in the entire real line. So remember that the range of x equals b to the y here is 0 to infinity, which is the domain of this expression. And the domain of this expression is r, which is the range of the logarithm expression here. Okay, let's clear this off and check out some rules for logarithmic functions. They have very similar rules that are analogous to the ones for exponentials, except we're dealing in the logarithmic class. So rather than operating through the exponent, we're now operating as over the same level and argument of the function. So when we have 1, log base b of 1 is 0 for any base, whether the base is 2, 1, 10, or the base we're going to very commonly use during this course is b equals e, which is Euler's number or the natural numbers, the natural logarithm. It gives us the natural logarithm, ln. So when you essentially plug in the base into the log of the same base, you get 1 back. So what this also says is this would say that ln e equals 1. That's another rule, since the base of ln is e. When you plug in a exponential function of the same base as the base of the log, you get back the thing in the exponent, and this follows directly from the property or the fact that the exponential function b of the x is the inverse of log base b of x. Again, b to the log base b of x is x by the inverse property. So these two follow from the inverse property. And now what we can do is we can work through some multiplicative rules. So let me clear this off. Sorry about that. So similar to the rules for exponential functions, we have multiplicative rule for logs, which says that if you're multiplying two things inside of the log, you can distribute the logarithmic function and add them. There's a quotient rule. Suppose you're dividing something inside a log by another. That means you could subtract the log of the denominator from the log of the numerator. And there's a power rule for logs that essentially says that if you're exponentiating an object inside of the log, you can actually pull the exponent out and set it out in front of the log and multiply the log of the thing inside by the exponent. There is also a natural log conversion formula that's fairly important. So if you have any base b log, you can always convert it to an expression involving natural logs, where, say, a is your variable, ln a, and b is your base. You just take the natural log of the thing inside and divide it by the natural log of the base. So let's check out some quick applications with compounding interest. Let PV denote present value, FV denote future value, R denote the annual interest rate, Q is going to be the frequency of compounding, as in monthly, quarterly, daily, annually. And T is going to be time in years. And there are two ways to essentially compound interest. One is the compound over discrete intervals, years, quarters, months, weeks, days, etc. Discrete means there's a discrete, the time period itself is discrete, and the compounding occurs infrequently. The other way is to continuously compound. That means you're always compounding all the time over incessantly and infinitesimally small intervals. So in this case, the future value is PV times e to the RT. And in this case, the second case, obviously the frequency of compounding doesn't come into play because Q here is essentially 0. It's infinitesimally small. Indeed, PV e to the RT is the limit of this top expression in 8, the right-hand side, as Q goes to 0. Okay. Or, excuse me, I said that wrong. Indeed, Q is infinitesimally small, so Q goes to infinity. Okay. How long in years will it take $1,000 to double in value if it is invested in an asset that yields a 2% annual return, and if interest is compounded at the following frequencies: each U.S. business day or continuously? So let's take a look at this. So how long in years? What we want to do is we're trying to solve for t, right? Let's actually set down what our variables are we have to work with. So we're looking for future value of 2,000. So we want the present value, which is 1,000, to double. We have R equals 0.02, so that's your 2% annual return. In A, we have Q equals 251. In B, we are actually going to use the continuous compounding formula, so it doesn't matter what Q is. So for A, we have Q equals 251. So that would be the business day frequency. So go ahead and take a moment and set up the problem and try to solve for T by isolating the numbers. And to do this, you're going to need to apply logarithms. Okay, continuing. Let's take a look at what happens if we compound each US business day. So 251 days. Let's set up the problem. So here we have our future value on the left. We're targeting 2000. We have present value here. This is our R, this is our Q, and this is Q times T. We need to somehow get this T down and isolate it. How are we going to do that? Well, first, what I'd like to do is note that if we take a log of both sides, we can exploit the power rule for logs and pull this entire expression out in front of the log of this thing. So we would exploit both the multiplicative and power rules for logs to pull that expression down. Okay, so now we can take a log of both sides. Let's clear the writing out. When we have a log on the right side, we can actually split up this object on the right side using the multiplicative rule. So we have ln 2000 on the left. Then when we use the multiplicative rule for logs, we have two separate objects, 1000 and this large parenthetical raised to the 251t power, which means we can split this up into ln 1000 plus ln of this large parenthetical. Finally, what we're going to do is we're going to apply the power rule for logs. We're going to take this 251t, we're going to pull it down in front, just like so. Having done that now, we can isolate t by using some common algebra. So going back one slide, note that we have an ln 2000 over here. On the left, we have a 251t times ln of this large object on the right. We can subtract ln 1000 from both sides. Then we can divide both sides by 251 times ln 1 plus 0.02 over 251. And when we do that, we get this object, which comes out to about 34.659. Note that I used a natural log just because it's most natural to do, and it's the logs we tend to use most in the business school environment. You didn't have to use a natural log. You could have used a log of any base. The idea here with compounding interest, though, is to exploit the fact that you have logarithmic functions that allow you to pull this exponent down to a level where you can do some more basic algebra on it and isolate it like so and come up with an expression for your final answer. A similar strategy is going to be employed to solve for the continuously compounded value of t, the length of time it takes for this asset to double in value. When we set this up, we use the continuous compounding formula, and that tells us that we have future value equals present value times e to the rt. If we take a natural log of both sides, natural log is even more natural here, since the natural log is the inverse of the exponential function, e. ln 2000 equals ln 1000 e to the 0.02t. Note that the multiplicative rule for logs can be applied again, where we split up this thing inside and insert a positive plus sign between the two separate logs. Finally, the inverse of e to the x and ln x allows us to write ln of e to the y equals y, where this y is being used here to represent a stand-in variable just for illustrative purposes. So the y is just this 0.02t. This means that the algebra here is going to be a little bit easier than it was before. And so now what happens is we can again subtract 1000 from both sides and divide by this number 0.02 to isolate t, and we get 34.657, which is close to the last answer we got if we go back a few slides, but not exactly. It's off by about 2 1,000ths of a year. So the frequency of compounding does make a difference in terms of how long it will take for an asset to appreciate. The more frequently you compound it, the less amount of time, but it's not really that significant. We're talking about 2 1,000ths of a year less. So we're compounding more frequently and the asset appreciated faster. The key point to take away from this is that you can use logarithms to solve power equations where variables are in the power exponent and to isolate them.